An electric field is a region around a charged particle where other charged particles experience a force. It is a fundamental concept in electromagnetism and helps us understand how charges interact at a distance. Let us start from basics. Consider a unit positive test charge placed at a point P in free space. There is no electric field or any electric charge around. There is no magnetic field around as well. Will this test charge experience any external force? Obviously not. The test charge will not experience any external force, so F equal to 0. Now let us place a large charge of magnitude minus q as shown in the diagram. Now the test charge will experience an external force. What is the magnitude of this external force? Coulomb's law states that magnitude of the force is equal to 1 upon 4 phi E multiplied by minus q by r square, where epsilon is the permittivity of the space and r is the distance between the charges. And the direction of the force is along the line joining test charges and minus q charge. Electric field is defined as the force experienced by a test charge of magnitude 1 unit at a point in space. When the source charge is positive, the field is outward, and for negative source charge, the field points inward as shown in the diagram. As an example, we shall calculate the electric field at a distance of 10 mm from a positive charge source of 1.6 10 to the power minus 7 coulomb in free space. According to Coulomb's law, electric field A equals kq by r square, where k is the Coulomb's constant of free space, q equal to source charge and r equal to distance from the source charge. Plugging in the values, you will get electric field A equals 14.384 10 to the power 6 Newton per coulomb. In the second example, we shall calculate the force exerted on an electron placed in an electric field of 14.384 10 to the power 6 Newton per coulomb. Force on electron equal to electric field multiplied by charge of an electron. Given values are electric field E. Charge of electron equals 1.609 10 to the power minus 19 coulomb. Plugging in the values, you will get force equals minus 2.30144 10 to the power minus 12 Newton. The negative sign indicates that the force is in the direction opposite to the electric field. In the example 3, there are 4 charges of q coulombs each placed at the 4 corners of a rectangle of side A. Calculate the magnitude of electric field at the center of the rectangle. The question can be explained with the help of a diagram. We have to calculate the electric field at the point O due to 4 charges of equal magnitude at the 4 corners of the rectangle. At the center O, the charges at the edges of the diagonal produce equal and opposite electric field at the center O, ultimately cancelling each other, and the net electric field at the center O is 0. In the example 4, 2 charges plus q and minus q coulombs are placed at the edges of a line of length A. What is the electric field at the center of the line? Magnitude of electric field at the point O due to positive q charge is equal to k times q by r square, where r equals a by 2. And the magnitude of electric field produced at the point O due to negative q charge is same as that of positive charge, but in opposite direction because of the charge is negative. Plugging in the values, you will get A equals 8k times q by a square. What are electric field lines? Electric field can be conceptually visualized using electric field lines. Electric field lines start from positive charges and end on negative charges. The density of the lines indicate the strength of the field. Electric field at a point due to multiple charges around can be calculated using the principle of superposition. According to this principle, electric field at a point is vector sum of electric fields produced by individual charges at that point. In the diagram, there is a positive and negative charge. At the point P, there are two electric field vectors along x and along y, produced by positive and negative charges respectively. The net electric field is the vector sum of these two electric fields as shown in the diagram. The electric field is either expressed in volts per meter or newtons per coulomb. You may have this question, how the SI unit of electric field volts per meter is equivalent to newtons per coulomb? How a physical quantity can have two types of units? Electric field is equal to force per unit charge and its unit is newtons per coulomb. Electric potential V is defined as potential energy per unit charge and electric field equals minus dV by dx, that is change in voltage per change in distance. So electric field equals 1 volt per meter. Combining these two equations, we will find that electric field can be expressed in volts per meter or newtons per coulomb. Do the electric field lines physically exist? Electric field lines are conceptual tools used to visualize and represent the electric field around charges. They do not physically exist in the sense that you can see or touch them, but they are incredibly useful for understanding and predicting the behavior of electric fields. The electric field lines indicate the strength and direction of electric field at any point. Think of electric field lines as contour lines on a map which represent elevation. The contour lines are not physically on the ground, but they help us understand the terrain on the map. The first important property of electric field lines is that the field lines originate from positive charges and terminate on negative charges. If there are no negative charges, they extend to infinity. The direction of the electric field line at any point gives the direction of the electric field at that point. For a positive test charge, the field lines point in the direction of the force it would experience. The density of electric field lines, that is how close they are to each other, represents the strength of the electric field. A higher density of lines indicates a stronger electric field. Electric field lines never intersect. If they did, it would imply that the electric field has two different directions at the same point, which is not possible. At the surface of the conductor in electrostatic equilibrium, electric field lines are perpendicular to the surface. This is because electric field inside a conductor is zero and any component of the field parallel to the surface would cause charges to move. Electric field lines can be curved, especially in the presence of multiple charges. The curvature of the lines indicate the direction and relative strength of the field at different points. Electric field lines do not form closed loops. They start from positive charges and end on negative charges or extend to infinity. What is electric flux? Electric flux is just a measure of how much of electric field passes through a given surface. If dA is an area vector, A is the electric field and theta is the angle between the two, E cos theta is the component of electric field normal to the surface. Mathematically, it is given as E cos theta dot dA integrated over the surface. In the diagram, a small surface is represented by dA vector normal to the surface. E is the electric field at the surface and theta is the angle between them. The angle theta indicates that electric field is not normal to the surface, it is inclined to the surface. EA cos theta is the total flux through the surface A. SI unit of electric field is newtons per coulomb and that of area is meters square. So SI unit of flux is Newton meter square per coulomb. To give you an analogy of electric flux, imagine electric field lines as streams of water flowing through a net. The electric flux represents the amount of water passing through the net. If the net is perpendicular to the flow, the flux is maximized. If the net is parallel to the flow, no water passes through and the flux is zero. Let us dive into Gauss's law. Gauss's law states that the total electric flux through a closed surface is proportional to the charge enclosed within that surface. Mathematically, Gauss's law is expressed as phi equal to q upon epsilon 0, where phi is the electric flux, q is the charge, and epsilon 0 is the permittivity of the space. We shall understand Gauss's law with an example. We shall calculate the electric field inside a uniformly charged sphere. We can use Gauss's law to find electric field inside a hollow cylinder. The electric field inside the cylinder is directly proportional to r, where r is the distance from the center. At the very center O, r equals 0, so electric field equal to 0 and linearly increases with distance r. On the surface of a uniformly charged cylinder, the electric field is maximum and is equal to q upon 4 pi epsilon 0 r square. In the example 7, a charge of 1.6 10 to the power minus 7 coulomb is placed at the center of a cube. What is the electric flux on each surface of the cube? To find the electric flux through each face of the cube, we can use Gauss's law, which states that electric flux equals total charge enclosed divided by permittivity of the space. In this example, charge enclosed equals Q equal to 1.6 10 to the power minus 6 coulomb. Total surface enclosing this charge equals 6 times surface area of each side of the cube. So flux through each face equals total flux divided by 6. Plugging in the values, flux through each face equals 3.01 10 to the power 4 Newton per meter square per coulomb. With this example, we have reached the end of the video. Thank you for watching.